My name is Peter from DQ Drives, and today I will be showing you how to get our motor controller M Classic from out of the box to running it with a motor and getting the motor to spin up successfully. So let's start with how I attached the motor and the motor controller together. Firstly, I took the motor controller out of the box and attached it to an improvised heatsink by firmly pressing it onto an electrically isolating heat transfer pad. Then I took out the included communications breakout PCB, gently wiggled it onto the pins, and soldered the pins to the motor controller. After that, it was time to prepare the motor. I used a hoverboard motor that was just laying around, stripped off all the old connectors, soldered on a new connector for the phase wires, and crimped on a new connector for the hall wires. And now, a small crimping ASMR. Now that we're done with the motor wiring, we continue with the motor controller wiring. For that, I cut in half some pre-crimped wires for the Hall sensors, soldered them onto the motor controller, and put them into the fitting plug. First, I struggled for a bit, but then it turned out just fine. At this point, it's as easy as plugging in the phase and Hall sensor cables and screwing on the supply, and turn on the power supply. Okay, now we are in the VESC tool and we can plug in the M Classic into my laptop. And we should see two serial devices coming up. This is a macOS specific, somehow it always shows up too. We can connect one of them and get this warning here that the VESC has old but mostly compatible firmware. This is expected because the VESC tool that I am currently using is made for VESC 7.0 and our controller is currently still shipped out with the 6.06 firmware. So we can just acknowledge it, and now we can go to the important settings. There's a ton of settings in the VESC tool, and I will just go over the very classic ones briefly. So these are the defaults. And we have the motor current max brake. I think they are pretty intuitive. So this is the maximum current that 100% throttle on your VESC will apply. So if you set this to 50 amperes or 60, then it will do 50 amperes if you give it full throttle. This also means that basically everything you do in the control of the VESC is limited to this maximum motor current. For our small little motor back there, I will just do it 30 amps. And here we have the absolute maximum current. This one needs a bit of explanation. So basically, to prevent any hardware damage, this current is constantly compared to the measured values. So not only the commanded, but the measured values of current. And if this absolute maximum current is exceeded, it will throw the VESC into a fault mode. Usually you set this absolute maximum current roughly 50% higher. Depending on the controller and your motor inductance and everything, this can also be closer together, but a very good default is 50% above the motor max current. Here we can set the battery current max and the max regen current. This is a calculated value that also will limit the motor current if the maximum battery current is reached. But as I said, this is a calculated value, and historically It's not too accurate, so I wouldn't use this as a reliable overcurrent protection, but rather as a gentle reminder to the motor controller to not drain the battery too much. For the voltage, this we don't care about currently because we're using a lab bench power supply. Here you can set ERPM limits. Maybe for those who don't know, the ERPM is the electrical RPM. So if your motor has multiple pole pairs, which most motors do, it does multiple electrical rotations per mechanical rotation. And for example, if you have 2 pole pairs, then 1000 mechanical RPM are 2000 electrical RPM. And here you can set a limit and a soft limit start, basically. So if you go with your RPM to 80% of the max value, it will start to slowly throttle in a proportional way. Wattage, you can set some power limits to use. This is kind of also related to the battery current, so it's not 100% accurate. And a very important tab is the temperature tab, because here you can set some throttling ramps. So MOSFET is always the power electronics on the VESC. So if they reach 85 degrees C, they will slowly start to throttle their power, and basically between 85 degrees C and 100 degrees C, it will do a proportional down ramp in the maximum current. So if you're right in the center, it will only do half the set motor max current. Same mechanism applies for the motor temperature. And here you can just set also different values. And this one also needs slight explaining. The acceleration temperature decrease basically decreases these limits for the acceleration phase of the motor. And the thought behind that is that if you use regenerative braking as your only braking system, as some VESC users apparently do, then you can basically throttle the acceleration more than you do the braking, so you can always get to a safe velocity by not running into thermal throttling while braking, but running into it while accelerating. But as our motor currently doesn't use any temperature sensors, I will just disable this, and the only thing that we need to take into account is the MOSFET temperature settings. Here, this is for integration with a VESC BMS, which we don't have, so we set it to none. And here we can set the minimum input voltage and the maximum input voltage. With this button, we can write the motor configuration onto the motor controller. And now, since we are using field-oriented control, we can go into the field-oriented control tab. And here we can put in a lot of parameters for our machine, which is the motor resistance, the inductance, and the inductance difference. So in other words, the saliency of the electrical machine, and also the motor flux linkage. These Kp, Ki, and observer gain values, they are calculated for us, so we don't need to put them in. But we don't need to know these values by heart. We can simply use the RL measurement function of the VESC to determine these values. And it warns us that the motor is going to make some noise but not rotate. This is expected, and I think you can hear that sound. We can do it multiple times. It always yields slightly different results, but getting these right is a good idea, but not absolutely necessary, because there are controllers, PI controllers, I should say, that basically regulate out the errors that you put into these measurements. Still, it's a good idea to do multiple measurements and maybe see if there's a trend or a clear center or values that appear multiple times. But for this simple motor setup, I will just use any of the measurement results. And now with these RNL measurements, we can do a flux linkage measurement. This will spin up the motor and thereby measure the back EMF constant. So as we can see, the motor is turning just fine. And we are getting a result of 20 milliwebers or 20 millivolt seconds. this is a usually expected result. So with the flux linkage, you'll usually be in the 1-digit milliwebers or lower 2-digit milliwebers. With the saliency, this is quite a high value, just as the inductance itself is. You're usually in the single to 2-digit microhenry range, and with the resistance, you're usually in the single to low 2-digit milliohm range if you have larger traction drive motors. But of course, as this is a very small machine, higher resistance and higher inductance are expected. Now we can use the apply button, and this will basically take all our measure values and write them into the config. And then we can write them onto the motor controller once again. And the last thing that we need is the Hall sensor calibration, I would say, because we just plugged in the Hall sensors in a random order. We have not yet gotten the info on how to decrypt the Hall sensor signal into an actual electrical position. This we can do with the Hall sensor measurement, or the Hall sensor detection, as it's called right here. This will turn the motor in a known electrical position and measure the reaction of the Hall sensors, and from that calculate the table values. This is done with a certain current, and just as for the flux linkage measurement, you usually don't want to have any large inertia attached to your motor, because that will definitely disrupt the measurement. But if your motor internally has a large inertia, then you can set the current slightly higher, which will increase the torque and thereby counteract the large inertia. So it's always a kind of balance, but 1/3 of the motor current max is a decent value usually. We can just measure these values. As we can see, the motor is turning very slowly in one direction, should change directions now. Yes. And if everything goes right, we get a green message right here that the detection result basically worked, or the detection worked. Then we get some values different from 255 in our measurement. These you cannot really validate by, or like in your head. And if you think these values are alright, you can again do these detections multiple times and see if the values are similar to each other. But I'm happy with this. I can apply it, so that writes the values to the table values, write the motor config one last time, and now we can see if the motor will work. So for that, we can go into the real-time data tab and activate the real-time data. Then we can see right here that we have 0 power, 28 degrees Celsius on the MOSFETs, and 30 volts of input voltage. And if we activate this little button right here, which is the keyboard control, we can use our arrow keys on the keyboard to control the current through the machine. This is the set current that we will basically command. So here we can set 3 amperes. So if I press the arrow up key, it will do 3 amperes positive current. If I press the arrow down key, it will do 3 amperes negative, so in the other direction. This is not a lot of current, but still I would say enough to get the motor spinning. So 3, 2, 1. This motor is spinning. Very nice. We can also look at the RPM tab and see we've got some RPM. And with this, I'd like to end the video because the motor is turning. We have achieved our goal. If you found this video helpful, please consider checking out other videos on our channel, and thank you for your attention.